are Team James Bond. This video will introduce our topic. The recent introduction of the corona diagnostic kit is a big issue. If the diagnosis of corona is made quickly, the spread could be greatly reduced. It is lab-on-a-chip technology that makes this possible. The necessity of lab-on-a-chip technology is increasing due to diagnose disease quickly with such microscopic samples is increasing. Therefore, our team determined that it is important to modularize lab-on-a-chip technology to improve its efficiency and functionality. And the most critical technology in modularizing is multi-bonding. We'll present a method for multiple bonding of lab-on-a-chip and verify its stability through tensile strength and leakage experiments.
The lab-on-a-chip is a device that enables laboratory research through nail-sized chips integrated into semiconductor technology, nanotechnology, and biotechnology in ultrafine circuits. This is a type of biochip that has advanced DNA chips or protein chips to the next level, and it is being developed and studied as a next-generation diagnostic and analysis device in various fields such as medicine, biotechnology, and the environment. In particular, disease-related analysis requires high sensitivity and reliable analysis of analytical techniques.
Modularization of lab-on-a-chip is a very important challenge. Let me give you an example to help you understand this.
TSV technology, one of the recently developed technologies in the semiconductor packaging business, is a method of inserting an electrically flowing pin using a central channel and transmitting electrical signals through this pin, unlike conventional wire bonding technology. This not only reduces a lot of connectivity when packaging semiconductors, but also provides faster transmission speeds in terms of space. This screen shows that the inlets and outlets of the lab-on-a-chip are connected to tubes and interacting. If the lab-on-a-chip is modularized, it will minimize the use of tubes and allow more efficient sampling.
There are many ways to bond to a lab-on-a-chip. The most popular method of bonding is thermopress bonding. This method has the advantage of making the chip more transparent by using heat and pressure, but it can damage the channel. Another method is adhesive bonding, which literally uses adhesive materials to bond chips. The advantage of this method is that homogeneous bonding is possible, but the advantage is that the adhesive can cause channel clogging.
Therefore, we will make up disadvantage of the excess bonding method by using photothermal bonding. Photothermal bonding has the advantage of having enough bonding power at low pressure. It is efficient because bonding is possible with just heating in the local area. It can also prevent chemical denaturation.
So far, we've learned about photothermal bonding. From now on, we'll explain the whole process of multi-chip manufacturing. Nanomaterial must be created before bonding. Mix the two substances in an appropriate proportion and use the liquid to blend well. and drop the material with a spoiler on the chip. And preheating it so that moisture can go away. And fix the chip through covering and bond with laser. At this point, photothermal effect occurs and bonding is formed.
When these multi-layer bonding chips are created, we can move fluids more efficiently. By modularizing, we can conduct microfluid experiments in the direction we want, the angle we want, and the speed we want. Multi-layer bonding with photothermal bonding will be a very useful technology for the Lebanon chip system.
This is the chip we will use. Raise two module chips. Apply photothermal to nanomaterials. Now, the Lebanon chip is ready to let the specimen flow.
Therefore, we will measure bonding efficiency through various experiments. There are three main methods for experiment.
First, tensile experiment. We make 3 multi-chips, but we will use 2 in the experiment. When a 3-piece chip is fixed by a tensile tester, it has geometry limitations. It makes it difficult to measure bonding's own properties. So, we will use 2 chips to measure bonding strengths, and then we will also use tensile tester's data to obtain the stress-strain curve. Second, rig test. We are going to set the inlet and outlet of the channel. By using microscope, we can measure how much fluid leaks according to the gap at a specific flow rate. Lastly, gap spacing. Gap spacing means that bonding creates a gap in the mating surface of the two chips. Gap formed by nanomaterial is very small, so it is impossible to measure with eyes or vernier calipers. Therefore, we will obtain photo data using the microscope and use the post-processing tool, ImageJ, to obtain the size of fine gap according to the accumulation of photos.
We are going to analyze the data obtained from the experiment as follows. We are going to conduct the tensile test according to the following variables. The variables we are going to cover are bonding time, nanomaterial amount, nanomaterial ratio, etc. We will be able to compare the bonding strengths and gap over pure bonding time, except preheating and covering time. In terms of nanomaterial, we will adjust the mixing ratio of CUS and RGO-PG and the final amount of mixture that goes into bonding. Finally, the data obtained from the experiment allows us to compare and optimize which bonding condition is strongest and best bonded. Also, we are planning to conduct a leak test with the final model. Leak test will be applied in 2 ways, experimental and simulation.
Lebanon chip made using our chip bonding technology can be applied to various places in the medical field. Diagnosis is the most basic step in treating all diseases. Our team's final goal is to combine chips in various diagnostic devices perfectly to optimize bonding so that it can function fully as a product. This will allow us to take a step further for human healthcare. This was Team James Bond. Thank you.